So today we will discuss about atomic theory of diffusion. Our lecture topic for today is atomic theory of diffusion. For that, we first will go through the different kinds of defects and then we'll understand the underlying mechanism with respect to atomic scale for the diffusion process in metallic systems. So if you look at different kinds of defects, defects are also having dimension. 0 dimension, 1 dimension, 2 dimension defects are there. So we'll start with 0 dimension defects, and that is point defects, or you can tell the vacancy. 0 dimensional point defects. So if you look at any perfect crystalline solid, in a perfect crystalline solid, all the atoms or molecules arrange themselves ideally. What does mean by that ideally? That they are having infinite periodic atomic arrangement. So there is a repetitive lattice vector after which the arrangement are almost are same, but there will be certain imperfections. So imperfections in such kind of crystalline solid. So thermodynamically, if you can classify, then what you will tell? Thermodynamically, you can classify them as equilibrium or non-equilibrium defects. So addition of certain defects up to equilibrium concentration decrease the free energy and making the material thermodynamically more stable. And these are in generally known as, suppose we can look at thermal vacancies, self-interstitials, impurities, or antisites or antistructure atoms. So these are the 0 dimensional defects. And equilibrium concentrations depend on the type of bonding and structure of the material. It is very important to understand that equilibrium concentrations actually depends on the nature of bonding and the structure of the material. And if you consider on the other hand, when addition of defects increase the free energy. So one kind of defects are decreasing the free energy, another kind of defects can lead to increase in free energy. They are called non-equilibrium defects. So you can understand now there are two kind of defects we are talking about, and we are classifying them as equilibrium or non-equilibrium defects. And addition of certain defects to equilibrium concentration, which actually results in the decrease in free energy. So in this process, they are making thermodynamically more stable material, then those defects can be named or represented by equilibrium defects. On the contrary, when addition of defect increase the free energy, they are called non-equilibrium defects. That means in presence of sufficient thermal energy, a system will try to decrease the concentration of these defects. If you look at non-equilibrium defects, so it actually, if you see them in the course of time, in presence of sufficient thermal energy, what will be the fate? System will try to decrease the concentration of these defects. Irradiation or deformation induced point defects, dislocation, grain boundaries, interfaces are the examples of such defects. So if you go for further classification, especially suitable for semiconductor, then you can go for the referring the defect and intrinsic, which is known as present in a pure material at equilibrium, or extrinsic induced by doping or alloying, or by presence of extended defect like grain boundary or surface. That are the two kind of nature defect you can get, intrinsic and extrinsic, in a electronic materials or semiconductors. So In this way, if you check, there are two kind of defects. So also we are already told that I told that defects are generally classified according to their dimensionality. Point defects are the zero dimensional defects, and they are different point defects such as vacancies, cells in interstitial solutes, and impurities or antisites. Now we are going to understand what is vacancies. If you see in the picture, there one atom is missing, or deletion of an atom or missing of an atom in the periodic arrangement, that actually leads to a vacancy. And when there is a vacancy, you can see there is a distortion. If you look at A, B, C, D atoms around the vacancy, there you will see one kind of distortion. So that is point defect or zero dimensional defect, one kind of zero dimensional defect that is called vacancy, and that actually leads to a distortion around itself. That is one concept. One should understand that how vacancy can lead to a distortion and what kind of distortion it will create. So during the vacancy understanding, what we understand, when an atom or components of that crystalline solid or are missing from regular lattice point, these are called vacancy. And now we are coming to another concept of zero dimensional defects or point defects. What is that? When these host atoms are located at the interstitial position instead of regular lattice positions. These are called self-interstitial. Instead of regular position, if this host atom is taken a position inside a interstitial, then you can tell that this is a self-interstitial, and you will see that major distortion around the self-interstitial. And in bottom, if you check that unit cell structure of lattice, and there you will find the interstitial positions, and interstitial positions are being occupied by a host atom, then you can tell that this is a self-interstitial. So again I am repeating, if host atoms are taking position at interstitial instead of regular lattice position, these are called self-interstitial. And you must remember, these are different from impurity atom present at interstitial site, which is going to explain few minutes after. Since in a typical metallic lattice, the size of a void at interstitial position is small to accommodate host atom displaced from a regular lattice point, the corresponding formation energy will be very high. From the picture already we understand there is a major distortion due to self-interstitial behavior. So why is it so? As in a typical metallic lattice, the size of a void at interstitial position is small to accommodate a host atom displaced from a regular lattice point, and the corresponding formation energy, if you look at, is very high, and the concentration of self-interstitial in a pure metal or substitutional alloy is negligibly small if you compare them. Therefore, we can tell that this kind of defect is relatively uncommon in metal unless the material is subjected to irradiation. So that cell interstitial kind of defects are not so common. You can tell that such kind of defects are relatively uncommon in metal. If not, there is a strong irradiation impact on the material. So vacancy on the other hand are dominant equilibrium defects in a metal. Already we understand that vacancy, thermal vacancy is a equilibrium defects, and you can tell that at above 0 degree Kelvin, any temperature above absolute scale of temperature, vacancy free material is impossible to find in reality. So we can tell that it is an equilibrium defects, and it actually helps to stabilize the material by reducing the free energy. Already we understood it. Now here you can see two kind of defects, that is Scotty defect and Franklin defects. So in order to understand that, we have to find out certain things. Suppose if you look at, depending upon the source, in case of semiconductor or such kind of electronic materials, point defects are classified into two categories: intrinsic as well as extrinsic. So when defects are created by displacement of own atoms in an impurity free crystals, they used to name as intrinsic defects. Therefore, vacancies, self-interstitial anticides are considered as intrinsic defects. We are understood that if you check that intrinsic defects are those defects which are created by the displacement of own atoms in an impurity free crystals. They are called intrinsic defects. Again, I am repeating, intrinsic defects are those defects when they are created by displacement of own atoms in an impurity free crystals. When defects are created by adding foreign atoms. So on the contrary, if you can check, when the defects are created by adding foreign atoms, they are named as extrinsic defects. Solutes, impurities are classified in that way. So you can check as an example, solute or impurities are examples of extrinsic defects. Now, here our objective is to understand Scotty and Franklin defects. So, in an ionic compound, if you check, unlike in metallic system, defects are present in ionic form. If it is ionic compound, defects also will be present in ionic form. So, defect chemistry for those material are very esoteric or complex because of the need for charge neutrality along with the mass conservation. When there is no ionic compound, normal metallic neutral compound or new metallic arrangement, then you are not looking at the charge neutrality. You are only looking for mass conservation. So now for defect chemistry, for such kind of ionic compounds, it is very, very complex. And because this is the need of because the need of the charge neutrality also essential along with the mass conservation and the fixed ratio of sites of anions and cations depending on the stoichiometric composition. So now we understood that there is really complex behavior we have to consider for defect chemistry with regard to ionic compounds. However, point defects, if we can discuss, then the influence of the diffusion of components, so intrinsic thermal defects can be created in different ways. And if you check that, suppose for a hypothetical compound, if you check that when equal number of anions and cation vacancy are created, then you can tell that that is Scotty defects. And you can see in the picture, ions leave their position, travel to surface, leaving behind vacant sites. Therefore, such defect creates volume expansion and leading to a decrease in crystal density. So, if you check Scotty defect and in order to get the Scotty defect, or the Scotty defect actually causing to a decrease in crystal density, or you can tell that kind of defect also leads to volume expansion. When equally many cations and anions transported from the surface to the interstitial position, such defect you can tell that anti-Scotty defects. They increase the density of the material. When movement of cations from regular site to interstitial position and creates vacant site and interstitial cation, it is called Franklin defects. You can see in the bottom picture. So when movement of atoms creates the same type of defect, namely vacant anion sites or anion interstitial, it is called anti-Franklin defects. So we can tell that if you take this kind of concept, as a matter of fact, all types of defects are possible in particular compound. In a single compound, in the same compound, all defects can be possible. That is the important concept one should remember. However, if you check, one type typically dominates over other based on favorable enthalpy of formation of that specific kind of defect. So most common defects are Scotty and Franklin defects, and we understood that. What are those defects? So in a crystal, a few minutes ago I told that in a crystal, all kinds of defects can be there: anion vacancies, cation vacancies, and cation interstitials. You can check in a single crystal, but this is a very important, which one going to dominate based on the enthalpy of formation of that specific defects. Now, in order to understand the detailed mechanism and mathematics of diffusion, it is very important to study a simple situation in which we can get an analogical understanding of diffusion process. So now we try to derive an approximate equation relating to diffusion coefficient D to the jump frequency. Jump frequency is very important. How atom jumping from one position to another position, that frequency, that jump frequency is very important in order to understand the diffusion process. So, and the jump distance. So we are now going to derive an approximate equation relating to diffusion coefficient to jump frequency and jump distance. Suppose you can consider a crystalline bar which has a concentration gradient along its y-axis as shown in the figure. If you check the figure, this is y-axis in the y-axis there is a concentration gradient for a considered crystalline bar. Now you consider only jump to left and right, that is those giving a change in position along the y-axis. Again, please consider two adjacent lattice plane. What is designated in the picture as a 1 and 2, and these two lattice plane, adjacent lattice plane, are apart by a distance, suppose beta. Now let there be a n1 diffusing atoms per unit area in plane 1 and n2 in the plane 2. So if each atom jumps an average of tau times per second, the number of atoms in the plane 1 that jump in short period dt is n1 tau dt. It is a very easy to understand. And assuming the jump frequency is the same in all orthogonal direction, 1/6 of atoms will go to the right to plane 2. So number of atoms jumping from plane 1 to plane 2 in a dt time period is 1/6 into n1 tau dt. The net flux from the plane 1 to 2 is, you can write as written in the slide, that 1/6 n1 minus n2 into tau equal to number of atoms per area into time. So the quantity n minus n2 you can relate to a concentration or a number per unit volume by observing that n1 by beta equals to c1 and n2 by beta equal to c2. So that leads to a derived expression that j equal to 1/6 c1 minus c2 in the bracket into beta into tau. But if you check, it is actually essentially all diffusion studies see changes slowly enough with the position. So you can write C1 minus C2 equal to minus beta del C del Y. So now the expression for J is becoming J equal to minus 1/6 beta squared tau del C by del Y. So this equation, if you check, it is very identical to the Fick's first law. So comparing first law and this equation, you can get the diffusion coefficient, and D is equal to 1/6 beta square tau. So diffusion coefficient is therefore can be determined by the product of jump distance squared and jump frequency. So you can see this expression that you can check by Fick's first law and the derived expression, and you can compare that, and then you can come to a inference that the diffusion coefficient D can be represented by 1/6 beta squared tau. That is, the diffusion coefficient is therefore represented by the product of the jump distance squared and the jump frequency. Now, just we have to remember certain things. It should be emphasized that tau was assumed to be same for the jump from left to right as from right to left. Thus, the flow down the concentration gradient does not result from any bias of the atoms to jump in the direction. So, if each atom jumps randomly, n1 greater than n2, therefore, there will be a net flux from 1 to 2 adjacent lattice plane, simply because there are more atoms on plane 1 to jump to plane 2. Then there are atoms on 2 to jump to plane 1. So these things are very, very important. Now we are going to understand the mechanism of diffusion, and mostly three mechanisms are important: interstitial mechanism, vacancy mechanism, and interstitiality and Claudian mechanism. So if you check the interstitial mechanism, here you can check that an atom is said to diffuse by interstitial mechanism when it passes from one interstitial site to one of its nearest interstitial site. More clearly, you can understand that if an atom is said to diffuse by interstitial mechanism when it passes from one interstitial site to one of its neighbor or nearest neighbor interstitial site without permanently displacing any of the matrix atoms. So it actually not going to disturb any of the matrix atoms, but it goes from one interstitial site to another nearest neighbor interstitial site. Okay, so this is the scenario where interstitial mechanism of diffusion are going to prevail. So in the picture, you can see that interstitial site of an FCC lattice. An atom would diffuse by an interstitial mechanism in such kind of FCC lattice by jumping from one side to another on the sub-lattice of the interstitial atoms. So you can check that and consider the atomic movement. You can understand that which must occur before a jump can occur. This is a very important statement. If you consider the atomic movements, then that atomic movement must occur or must take in place just before a jump can occur. And the figure it is showing that an interstitial atom in 100 plane of 100 plane of a group of spheres packed into the FCC lattice. Before the atom level 1 can jump to nearest neighbor site 2 of the matrix atoms, level 3 and 4 must move apart enough to let it through. That is very important. Actually, if one rises out of the plane of the, if you check out of the plane of this slide, slightly as it starts towards the 2, there is a partially formed channel available. So you can check, nevertheless, an appreciable local dilation of the lattice must occur before the jump can occur. It is this dilation or distortion which constitutes the barrier of an interstitial atom changing the size. The basic problem in calculating in jump frequency is determining how often this barrier can be surmounted. This is an important thing. So you can tell that the dilation or distortion which constitutes the barrier to an interstitial atom changing site, it is very important. It's very important. And the interstitial mechanism, what we discussed now, it operates in alloy when the solutes normally dissolve interstitially. Suppose you can check carbon in alpha or gamma iron in case of steel, very well known alloy, that is an interstitial alloy. Now we are going to understand the vacancy mechanism. In case of vacancy mechanism, if you want to understand, then you have to understand how vacancy is created, what we already have discussed. And in all crystals, some of the lattice sites are unoccupied. If the crystals in the temperature just greater than absolute zero. These unoccupied site you can name as a vacancy, what we already understood. Now in the figure, you can check that nature of the constriction which inhibits motion of an adjacent atom into a vacancy in a FCC lattice. If the undistorted lattice is taken to consist of close-packed spheres, if you check in the figure, spheres of a diameter d, the equilibrium distance between the restraining atoms will be 0.73 d. So you can check that distortional energy put into the lattice in moving an atom into an adjacent vacancy is roughly equal to the energy required to move a carbon atom from one interstitial sites to another in the same FCC phase. The reason that iron diffuses so much more slowly than carbon is that which each carbon atom always has many vacant nearest neighbor interstitial sites. Then the fraction of vacant iron site is very small and each iron atom must wait a very significant amount of time before a vacancy becomes available. But in BCC lattice, the barrier for the jump of one atom into a vacant nearest neighbor site is much more complex. And the extended barrier of two sets of triangular barriers, the vacancy mechanism is thought to be the mechanism of self-diffusion of all pure metals and for essentially all substitutional solutes in alloys. And this slide is dedicated to understand how barrier is important with respect to atom to go to the vacancy site. This barrier comes or interstitial atom to empty interstitial site. There will be a barrier. There will be certain height of the barrier that has to be overcome in order to sustain such kind of diffusion process either from vacancy mechanism or interstitial mechanisms. Now we are going to learn about interstitiality or Claudian mechanism. Solute atoms which go into solution in a metal as interstitial are appreciably smaller than the matrix atom. So you can understand if solute atoms are appreciably smaller, then such kind of interstitiality or Claudian mechanism are come into play. So if you check this question, if a relatively large atom such as solvent atom gets into an interstitial, now we are talking about self-interstitiality. If a large atom such as a solvent atom gets into an interstitial position, how will it move? What will be the mechanism underlying for the movement of such kind of solvent atom which goes into interstitial position? It will produce very large distortion if it jumps from one interstitial site to neighboring interstitial site. Since the size of the atom is almost equivalent to the matrix or it is equivalent to the matrix, so it will produce very large distortion. The jumps which produce very large distortion occur very less frequently, because if it is producing large distortion, so it is going to take place very infrequently. So another diffusion mechanism which produces less distortion must be dominated or could predominate. So one jump process which gives less distortion is the interstitiality mechanism. And consider the interstitial atom if you check. So it is said to diffuse by interstitiality mechanism if it pushes one of its nearest neighbor atom into a interstitial position and occupies the lattice site previously occupied by the displaced atom. This distortion involved in this displacement is quite small, so it can occur with relative case. So this is a relative things. There is only a distortion, but it is smaller than what we had discussed previously. And the mechanism has proved to be dominant one of the diffusion in the diffusion of silver in silver bromium. So you understand that even you check with the pure FCC crystals, the atoms are all same size and distortion associated with the configuration shown in the picture. If you check the picture, is quite large. So it has been seen that if you check as FCC as example in copper, probably for all FCC metals, the accommodation of the extra atom in such a manner, if you check in the figure, still another interstitial configuration is there, and that is called Crowdian. It has extra atom placed in the close back direction. If you check that in this picture, you can understand. In the picture, 110 plane of FCC lattice with two atoms sharing one side. The difference between A and B is just interstitiality charm. So now you understand that displacing several atoms from their equilibrium position, it creates a distortion, and that actually leads to Crowdian things. And another picture is a 111 plane of FCC lattice showing Crowdian. So if you check such configuration, it resembles with a kind of dislocation structure. Later on we will understand that. So with this multiplicity of configuration of interstitial atom, it can be understood, or it can be said, or it is well to point out that interstitial atom means only that there is one more atom than there are sites in the given small region. That is actually interstitial atoms concept. Now we are coming, because now position are changing by atom. One atom goes another interstitial site. So this is the end of the day. You have to take into account that interstitial atom means only that there is one more atom than there are sites in a given small region. So similarly, vacancy need not, but site is vacant, but the region contains one fewer atom than the sites. So now we have to get the overall region concept to understand such defects, because diffusion compels us to think like that. The diffusion underlying mechanism compels us to think like that. Thank you. Today's lecture is over.